So today's lesson is going to cover exponential growth and decay. There's some vocabulary here we need to go through. An exponential function has the exponent as your variable. So that's how we know it's an exponential function. The other number is called the base. An asymptote is the invisible or imaginary line that our graph cannot cross. So here our asymptote is right on the y-axis. Now this can be moved up or down. Exponential functions can either grow or decay. The way we know the difference between growth and decay, it's growth if your base, remember your base is down there, is larger than 1. So here we have f of x is equal to 2x and it's growing up. Decay is if the base is less than 1. Now granted the base has to be greater than 0. So if it's any fraction less than 1. So here we have exponential decay with the base of 1/2 to the power of x. And it's decaying down. Now notice both of these don't cross that y-axis, and the reason being is that there's an asymptote there. Our growth factor is the base when it's greater than 1, so that's how we're growing. Our decay factor is the base that is less than 1. That's how we're shrinking. Those are the factors. If our base is 1, then we just have a straight line. This is the basic formula. We have y is equal to ab to the power of x minus k plus c. It's important you know what all these do. So we just said our growth or decay factor, or rate of decay, is the b value, our base. The a value in front, that stretches it. It's a vertical stretch. It's going to affect our y-intercept, and if it's negative, it reflects it across the x-axis. The c at the end is our vertical translation. This should look familiar. The c at the end moves it up and down. The k on the inside moves it left and right. That's our horizontal translation. Now remember your rebellious numbers. If you have a negative k, that means you're going to move to the right. And if you have a positive k, that means you're going to move to the left. A couple important things to note. A negative x reflects across the y-axis. So if our x value is negative, this is what it's going to look like, this blue one here. Now if we have a negative y, that's going to reflect over the x-axis. It says the parent function for the graph is shown. So we have a graph right here. First we need to figure out what our base is. When these cross the y-axis, it'll always be at 1 unless we move things up, down, left, or right. The reason being, any number 2 to the power of 0 is equal to 1. 3 to the power of 0 is equal to 1. 4 to the power of 0 is equal to 1. Any number raised to the power of 0 is 1. So when our x value is 0, we'll always cross the 1 unless we move. Then we need to figure out what our base is. So let's take a look. If I move over 1 to the right, how far up do I go? Well, I go up to 2. So 2 to the power of 1 is equal to 2. This means our base is probably 2. Now we can double check this by going one step farther. If I move over 2, how far up did I go? Well, it went up 4. So 2 squared is equal to 4. So I know that the parent function is going to be y is equal to 2 to the power of x. Now they tell me a translation 9 units to the right, and then a translation 3 units up. So it's going to look like this. Because they said 9 units to the right, and I know that the x values are rebellious, I'm going to say a negative 9 in with the x. And it said up 3 units, so that means I can go up 3 units. So this is what your new formula will look like. Now, if we want to look on a graph, we can change the numbers on Desmos. Here I have y is equal to our exponential function. We just said that the a value is 1, that didn't change. We said our base is 2, so I have the base as 2. We said the k value was going to be 9. We're going to move that 9. Now notice it's a positive 9 here because there's a negative in my equation. Because the equation has a negative value there, it would be saying x minus 9. And then the c was 4, so the c is going to move up 4. Now what this has done to our graph is it's moved up 4, so our horizontal asymptote is at 4, and it's moved it to the right by 9. Now, the next one says graph the function of f of x is equal to 3x minus 2 plus 4. So we're going to go back over to Desmos. They said our base is going to be 3, our k value is going to be 2, and our c value is going to be 4. So what that did is it moved the graph up 4 and to the right 2. Now, they want the domain and the range. The domain and the range are pretty straightforward. Domain is always going to be all real numbers. So the domain is going to be all real numbers. Now, remember, there's another way of writing this. We can also write the domain from negative infinity to positive infinity. Then the range can be written in two ways also. So the y value, let's look at the y value. It's coming down to 4. Now if you notice, it's never going below that 4. And technically it's never actually touching that 4. So what we would say is the range is going to be y greater than 4. It's going up and it's bigger than 4. The other way of writing that is the range is going to be from 4 to positive infinity. Now the next one, they say graph the function f of x equals negative 3x plus 2. Give the domain and range. Now notice, we're not moving up and down. However, we do have a negative in the front. So our a value here is negative. What that's going to look like, if I have a negative a value, it's going to flip the graph upside down or reflect it over the x-axis. Now this is what it's looking like. See how the graph is flipping? So now the graph is pointing down. Then they told us that we had an x plus 2. What that's going to do is it's going to move it 2 to the left. Now the reason why I put a negative 2 for the k is because there's already a negative in my equation. So a negative and a negative is going to give me a positive. So this is our new graph. Now the domain is always going to be the same thing, all real numbers from negative infinity to positive infinity. The range, where are we starting? We're starting at 0 and we're going down to negative infinity. So our domain is going to be from negative infinity to positive infinity. It's always the same thing. You should get the answer right. The range was pointing down. Where did we start? We started at 0 and then we went down to negative infinity. The other way of writing the range would have been y is less than 0. Now there's several important formulas related to exponential growth and decay. This is the basic formula where you have the final amount, the initial amount, and then you have one plus or minus your increase or decrease. If you're growing exponential growth, then it's going to be plus your rate of increase. If you're decreasing, something's getting smaller, exponential decay, then you're going to be subtracting. And then the T always stands for time, the number of time periods. Another important formula is compound interest. So this is when we put your interest back in your bank account every single month. So the compound interest is how many times you're putting the interest back in. And this is the formula again. You have the total amount or your final amount, your principal, which is also your initial amount, 1 plus the rate, but now we have over n, and then time is also multiplied times n. And n means the number of times the interest is compounded in a year. So that means monthly is going to be 12 for n. If it's weekly, it's going to be 52 for n. If it's hourly, then you have 365.25 days in a year times 24 hours in a day gives you 8,766 for your n. So your n is based off of how many times you're compounding per year, because time is always counted in years. The next formula that's important and you need to know is continuously compounded interest. And we just call it A equals PERT. A is your final amount. P is your principal or your initial amount. E is simply a constant. It's a number. Think of pi. We all know what pi is, 3.14. Well, E is a constant, 2.718, and it keeps going on forever. Now, you'll never calculate E by hand. You'll always use your calculator for that. Again, R stands for your rate or your interest, and T is time. Now let's do a few examples using these formulas. A population of 140,000, so that's your initial amount, grows at 5%, so your rate is 5%. But we never will use percentages. Remember, we have to change it to decimal form. And your time is 15 years. It says, how much will the population be after 15 years? So first we need the equation or the formula. If we go back to our list of equations, it doesn't say anything about compounded interest. So we're not going to use continuously or the compound interest. We're simply going to use the normal exponential growth and decay. So that means our final amount is equal to our initial amount times 1 plus, the reason why I'm using plus is it's growing, 0.05, because that is our rate, raised to the power of t, and our time is 15 years. Our initial amount was 140,000. Now, instead of saying a of final, we can also say y if we're going to be graphing this. So we can say y is equal to 140,000. 1 plus 0.05 is 1.05 raised to the power of 15. Then you simply plug that into your calculator. When you plug that into your calculator, you get your final amount for the population is 291,050. The next question says, a quantity of insulin used to regulate sugar in the bloodstream breaks down by about 5% each minute. A body weight adjusted dose is generally 10 units. First, they want us to write a function to represent the amount of dose that remains. In order to do this, we need to figure out what our initial amount is. Our initial amount is 10 units. And what our percentage is 5%. Now, we're going to be decreasing because it's breaking down. So we would say our final amount is equal to our initial amount times 1 minus the 0.05, which is our rate, times time. Now 1 minus 0.05 is going to be our 0.95. So that's part A. Now part C says how much insulin remains after 10 minutes. So we just plug 10 into there. Some of you are wondering how we can use minutes, and that's because the question gave us 5% per minute. You plug that into the calculator, you get A of 10, meaning the amount after 10 minutes is equal to 6 units. Up above, we mentioned the continuously compounded interest. Here's the formula again. Remember, E is just a constant that you're going to use in your calculator. Next question says, find the amount in a continuously compounded account for the following condition. They give us the principal is 2,000, the annual rate is 5.5, and it's 5 years. So we set it up like this. Remember, 5.5% has to change to 0.055. So we have 2,000 times E raised to the power of 0.055 times 5. And that's going to give us, after you plug it into your calculator, 2,633.06. Remember, because it's money, you always are going to have 2 decimal points. The next question is similar. They tell us 5% for 10 years at $1,000 initial investment. You would set it up like this, which gives you a final answer of $1,648.72. For the last problem, if you have $500 and you can invest it at 5.25% for 40 years, how much money would you make after 40 years? Set it up. A of 40 for our time is equal to our initial investment of $500. E to the power of 0.0525. Make sure you change that percentage correctly. That's usually a common mistake. Times 40. When you plug that in, you get $4,083.08.